Internet went out like during the last 10 minutes of my last class, so I hope that doesn't happen again. We will see. Okay, so we're going to continue with sequences and series. So I'm going to go put us into writing mode. Boom, there we are. Oh, I should also highlight myself. That way everyone sees me. Okay. So we are learning about a new type of series, which is called the alternating series. And I guess one of the things that I should point out, and you should put, hopefully you have in your notes, is that up until now, most of our series theorems, in other words, those rules we have about calculating series, they have assumed that the terms are positive. And usually also that they're decreasing. So if you go back and look at your notes, you'll see that I think, let's look, I'm just going to sort of scroll through the book. If you look at the comparison test, you will notice that it's required that all the terms are positive. You can't have some of them be negative. If you look at the integral test, no, that one doesn't require that they're positive. If you look at the divergence test, no, that one doesn't recur. Okay, apparently it's really just the comparison test. My bad. I guess really I should put this with the comparison test required that the terms are positive. And that they're decreasing, I think. And then other ones, other theorems, required that terms are decreasing. Okay, so now we're interested in trying to come up with some stuff that will allow us to deal with sequences that have negative terms. So we're going to first start by talking about something called the alternating series. And I have made an allusion to this before. So let's say you have the sum of n equals 1 to infinity of negative 1 to the n. So do you remember when we talked about the sequence of negative 1 to the n? A1, if you plug in 1, negative 1 to the first power is negative 1. If you plug in 2, negative 1 squared is positive 1. If you plug in 3, a negative 1 to the third is negative 1. So how's this always going to work with this sequence here? How would you describe when it's negative and how it's positive? Yeah, exactly. So all the even powers will be positive, all the odd powers will be negative. So what this becomes is negative 1 plus 1 plus negative 1 plus 1 plus negative 1 ... forever. And this actually leads us to sort of a problem. Because what do you want to say the answer is for this? If you look at these terms, what would you be tempted to do? Yeah, you'd be tempted to say they're 0, but under what would be your justification? I'm actually going to write in one more term to hopefully point you in the direction of that justification. So definitely, well, not having necessarily do with telescoping. Why would you want to say that negative 1 plus positive 1 plus negative 1 plus positive 1 plus negative 1 plus positive 1 forever and ever and ever is going to be 0? Well, actually, no, these numbers don't go to 0. They're all negative 1 and positive 1. Okay, cool. Okay, that's a better way of saying it. You could say is that you can put the pairs together, and what can you say about that pair? They cancel. And then you could look at that pair, and they cancel. And you could look at that pair, and they cancel, right? So you'd want to say that that's 0. Cool. But what if you decide to look at it this way? Let's forget that first negative 1. and then write 1, and then write -1, plus 1, plus -1, forever and ever. I'm not going to touch this one. Now what will happen with these two? What will happen? And what will happen with these two? They will. And everything else afterwards will cancel. And what will I be left with? Ha! See? Do you see? This one you're like, equals 0. This one you're like, equal to -1. Which one is it? Okay, so like, that's why you have to be very careful about when you have negative terms. Because when you have an infinite number of things that you're dealing with, you can just forget about the first one and everything afterwards will cancel, leaving you supposedly with just that -1. Okay, that's actually the reason why when we calculate what the series goes to, what are we supposed to do that we are not doing here? So like, how are you actually supposed to look to see if this series converges or not? Yes, but taking the limit of the... What are we actually supposed to take the limit of? Just to make it very specific. Okay, it does involve taking a limit, but taking the limit of what? Not the ANs, because the ANs are the individual terms. Not quite. Very close, though. Remember that the ANs are the terms of the sequence. And then the series, okay, so it's the partial sum. You take the limit of the partial sum. So remember, you start with the first one, you add up to k, and then you let k go to infinity. Okay, and there actually ends up being a lot of weird stuff that happens if the terms are negative, basically. Okay, so that's what we're going to talk about today. And our first introduction to this, and this is chapter 5, section 5. Our first introduction to dealing with negative terms, basically, is this thing called the alternating series. Okay, so the alternating series, you can sort of see what it's like. It alternates between positive and negative. Okay? So any alternating series is going to have this form. So any alternating series has the following form. Okay, so you're going to have a sum from n equals 1 to infinity. And then what you're going to have is -1 to the n plus 1 times bn, where bn is some other sequence. So an alternating series means that you take some series and then you start alternating how the terms are positive or negative. Okay, so because the power is n plus 1, is my first term going to be positive or negative? So you have this n plus 1 right here. Because when you plug in 1 into n plus 1, you're going to get that squared. So you're going to get b1 minus b2 plus b3 minus b4. So all of the evens will be negative if you have n plus 1. So n plus 1 makes the even terms negative. And then ... afterwards. Okay, so if the evens can be negative, the other possibility is that the odds are negative. Okay, that's not hard to get that to happen. You also have a sum from 1 to infinity, and you'll just have -1 to the n times some bn. Because now, when you plug in n equals 1, you get -1 to the first, and that will give you a minus b1, and then a plus b2, and then a minus b3, plus b4, minus ... Okay, so notice, having the power of n here, that means now that the odd terms are negative. So is that sort of making sense that you can change the power there to basically determine whether, basically the order to how it flip-flops, right? Whether it starts negative and goes positive, or whether it starts positive and then goes negative. Okay, cool. Making sense so far about our about what it means to be an alternating series. Okay, cool. Okay, so okay, so let's do our first example for one of these. Okay, so what do you know? Or here's a better question. What is the name of this series? Nice, it has called the harmonic series. And we know that the harmonic series diverges. Okay. So now we have another series that we're going to talk about, which is very, very similar to it. It is basically the same thing, but what you get is -1 to the n over n. Okay, wait. Okay, wait. Maybe I'll show this. Okay, wait, I'm reading something wrong here. Give me a moment. What the hell? Okay, that's that one. Okay, my bad. I want this to be n+1 here. Okay. I guess we won't prove this. I'm just going to tell you, the harmonic series diverges, but the harmonic alternating series converges. And we're going to explore why this happens, basically. And actually, let's sort of go through it. So the way we need to figure this out is, remember, you determine convergence by looking at the limit of the partial series. Okay, so let's come up with our formula for the partial series. Our SK is the sum from n equals 1 to k of -1 to the n+1 over n. Okay. Oh yeah, that's actually pretty hard to talk about that. We're going to skip that. That is really hard to show why this works. There's an interesting aside in the book where they actually have a discussion of being able to show why this converges, but it's sort of tricky. So I guess I'll try to just do it by walking us through the terms. So because it's n+1 in the power, what do you know about how it flips back and forth between positive and negative? Yes, rest, but I don't want to scroll back up. Which one is it? Someone just throw it into the chat. Sometimes it's easier to outsource part of the thinking. Thank you. The first number is negative. So you get 1 over 1 minus 1/2 plus 1/3 minus 1/4 and so on. So let's say that we stop with k as some even number. So the odds would be negative. So if k is even, okay, so this one is odd, Okay, so the evens would be negative. So we would have plus dot 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 minus 1 over k. Okay, and then what you can actually do, the way that you can go through this, is that you can rewrite this by looking at them in pairs. So like if you really wanted to prove that this would converge, you would look at these first two terms and you notice that this one would be 1/2, and then the 1/3 minus 1/4, that's going to be some other smaller number. Like, I don't know, let's just make something up. It's going to be, or let's actually calculate it. What is it? We would put it over 12ths. 4, 3, oh, so you get 1/12. And then, actually, let's just put a couple terms. Maybe we can like see what they go through. So then you would get 1/5 minus 1/6. Is that going to be out of 30ths? Is the least common denominator of 5 and 6 30ths? I want to say yes. Okay, cool. So that's going to be 6 minus 5. So you see how that's like 1/30th? Oh, that's cool. I get it. Someone just messaged me that their internet's cutting out. Yeah, it's no big deal if you drop in and out. I understand. My internet went down earlier. So anyways, so you have 1/12, 1/2, 1/12, 1/30th. Yeah, is Comcast the same as Xfinity? Oh, yeah, it was trash, yes. I've discovered that. My AT&T was way better. So anyways, you look at this. So basically your partial sum is going to be like 1/2 plus 1/12 plus 1/30th. And then what you could actually do is you can find, you can compare this to another sequence, such as this one. So if you look at 1/2 to the n, the first terms would be 1/2, and then what would the second term be? 1/4, and then what would the next term be? 1/8. So this one is the same size as that one. This one is actually smaller than that one. This one is also definitely smaller than this one. So if every term in this sequence is smaller than the terms in this sequence, and this one converges, what can you say about the alternating harmonic series? That it will also converge. Right? So this is basically the, what's the word? We're using the comparison test here. You could actually compare the alternating harmonic series to this particular geometric series, which you know converges. So boom, you can figure out pretty quickly that it converges. I'm gonna like skip over like all of the details, and I'm just sort of showing you like it makes sense that it should converge. Okay. So let me show you how a theorem that we're going to use to show whether an alternating series converges or not. So this is called the alternating series test. Okay, so let's say you have an alternating series of either of these forms. You have -1 to the n bn, or you have -1 or you have the sum from n equals 1 to infinity of -1 to the n plus 1 bn. It doesn't matter if it starts at negative and goes positive, or it starts at negative and it doesn't matter where the negative starts. Sorry, my brain is like going at the wrong speed. My mouth is sort of just saying things, and my brain is like doing something else at the same time. I'm so sorry. It must be crazy. Interestingly enough, if you have n minus 1, that gives you the same thing as n plus 1, and let's just sort of like compute it. Because if you start off by plugging 1 into n minus 1, what are you going to get? 0, and what? Oh, I see what you're saying. That would probably not be an alternating series. Let's actually look at that. That's a good question. So the question is, if you have the sum from n equals 1 to infinity of -1 to the n minus 1 bn, what does that give you? So if you plug 1 in 1 minus 1 is 0. Negative 1 to the 0 is 1, so you would get b1. Okay, now when you plug in 2, 2 minus 1 is 1. Negative 1 to the 1 is negative, so you get minus b2. Okay, so then and then let's just plug in the next number, 3. 3 minus 1 is 2, that's squared, that'll be positive, positive b3. So it looks like, yes, it is an alternating series. And how does this one work, the n plus 1? If you plug in 1, you get squared, which will be positive, so you get b1, and yeah, negative b2. So you get the same thing. That's actually pretty cool, huh? So yeah, it doesn't matter. That's actually why we only have these two forms, because actually, you can also have this one like this. You get a like negative 1 to the n plus 2. If you're as long as the difference between these two numbers is 2, they'll be the same. Because notice n plus 1 and n minus 1, they differ by 2. So either way though, that's why we only really care about these two, because any alternating series can be written in this form. It also could be written in the other forms, but those would just be more confusing. So let me erase these. Erase that. Okay, so let's say you have an alternating series like this. So it will converge if. So these alternating series will converge if, and then now there's some requirements to figure this out. 1. Let's say that the term bn plus 1 is positive, and it is smaller than the term that came before it for all n greater than or equal to 1. So what this is basically telling you is that if you forget about the fact that they're positive or that the terms go positive or negative, because I hope everyone can see that what we have going on here, the negative 1 to the n, that's what makes the stuff negative. Or the negative 1 to the n plus 1. The bn terms, those are all assumed to be positive. So it's the part that I highlighted in green that switches it back and forth between positive and negative. Yeah, a really quick way of saying it would be that the absolute value of your negative 1 to the n bn, or absolute value of negative 1 to the n plus 1 bn, is decreasing. But you can just say here that the bn terms are decreasing. This is called a recursive definition. What this is saying is that, hey, if you choose some term bn, then the term bn plus 1 had better be smaller than it. And that had better be true for all of the terms, which is equivalent to saying that they're decreasing. But it's often more useful to describe it this way, because it allows you to compare two terms as opposed to having to look at all of them. We talked about this before. You can have things which are decreasing that are not fractions. Remember I gave you the example of the increasing roots? But basically, yes. Like what you're thinking is intuitively correct, but technically wrong. Okay, so as long as your terms are decreasing, and 2, no, because remember the example that I came up with was not square roots. It was like take the square root, take the cube root, take the fourth root, take the fifth root. Okay, actually, okay, yeah, sort of. Yes. So yeah. Let me write that. I'll write a couple terms so we can talk about it. This is like a cool discussion, so I'll allow it. Like I'm thinking of that guy from Community. Has anyone ever watched Community and seen the meme where the Asian dude who teaches Spanish is like, I'll allow it, and he's like wearing the sombrero? Yeah, Chang, there we go. So yes, it's true that the square root of 2 is 2 to the 1/2. The cube root of 2 is the 2 to the 1/3. The fourth root of 2 is 2 to the 1/4, and so on. However, that fractional part has nothing to do with like literally being able to not write the number as a fraction. Like, for instance, 2 to the 1/4, I'm pretty sure that that's an irrational number which can never be written as a fraction. But yeah, it has a fraction in it. Oh, so you mean like... So for the p-test, like that works as long as your p is bigger. It converges as long as p is big. It converges as long as p is bigger than 1, whether it's a fraction or not. All the fractional parts would fail. Yeah, unfortunately this has nothing to do with that though, because this is talking about the terms of the sequence. Whereas this here, we're talking about like if you were to add all the terms of the sequence. And actually, that's sort of like one of the hard things about learning all this, because there's sometimes we're talking about the sequence, which is just the terms themselves, and then sometimes we're talking about the series, which is the sum of all of those terms. So it's hard to know, like when we're talking about it, sometimes like, oh, when I talk about a fraction, like, do I mean like literally the fraction as a number, or do I mean like the fractional, p as a fraction or something like that? Okay. So let's erase that part. So our second thing that must happen if we want this to converge is you need the limit of the terms of the sequence to go to 0. Boom. If those two things happen, then you are good to go, basically. So if the terms are decreasing, and they have to decrease every single time, basically. It's like, you can't have something like this. Okay, why does this not work? If you look at the terms, this would be your bn's. Why would this fail the alternating series test? Well, no, it's okay that they're all positive. Because your bn is the positive part. Remember, the alternating series test is you take that bn and you multiply by -1 to the n. There's something else going on here. Exactly. It has to get smaller every single time. Here, it gets bigger, and then it gets smaller, and then it gets bigger, and then it gets smaller, and then it gets bigger, and then it gets smaller. Unfortunately, the alternating series test requires that the terms are all decreasing. It has to decrease every single time. So if you look right here, it increases. If you look right here, it increases. It does, however, decrease from this one to this one. It does decrease from... Actually, I highlighted the wrong thing. Okay, it increases, and then it decreases. And then it increases, and then it decreases. The alternating series test is very specific that they have to get smaller each time. Could you combine 2 at a time so that they're all decreasing in groups of 2? Possibly yes, but as written, no. Which was what you would do if you wanted to like make this work, yes. However, you would see that, this is where it gets confusing, the -1 to the bn there. So because it's -1, which is the one that starts positive? I want to use the one that starts positive. The one that starts positive is n plus 1. Okay, cool. So let's make this -1 to the n plus 1. You would get 1/2 minus 3/2 1/2 minus 4/3, 1/3 minus 5/4, and so on. And then it becomes like really confusing because you have to group them, right? So I'll just say that it's difficult. Okay, so let's do an example of this to show that it works, or to prove some things converge or not. Alright, so we shall do an example. How would you actually use this in practice? So let's say you had the sum from n equals 1 to infinity of -1 to the n plus 1 all over n squared. So looking at this, it looks a lot like this, right? Does everyone agree? The 1 over n squared, which is a p-series, and it would converge because your p would be bigger than 1. Okay, but unfortunately, you know, this has this alternating term, so now you have to sort of wonder like, oh shit, like what's going on? It's not the same exact thing anymore. Okay, so what do we need to do? Well, we first need to show that bn plus 1 is less than or equal to bn. Okay, good luck with the vaccination appointment. Okay, so you plug everything into the formula. Your bn plus 1 is going to be -1. Actually, sorry. I guess what we should remind ourselves here is that, remember, the bn part is the part without the negative. So our bn is just 1 over n squared. Right? This part just does the alternating, and it's the rest of it that we're calling bn. I wouldn't say that's the an. I would think of it more like this, that you should, this is how you should write it. You should split it up into two parts. We have a -1 to the n plus 1 part, times, and then times 1 over n squared. This is the part that you're calling bn. Anything with a -1 to the power, you just forget about. Does that make more sense? It's the part that actually generates the terms of the sequence. The -1 part just flips the sign of the sequence from positive to negative, positive to negative. Cool. So b to the n plus 1, that is 1 over n plus 1 squared. And b to the n is just 1 over n squared. Okay, so we need the one on the left to be less than the one on the right. They both have the same numerator, so what you can do is compare the denominators. So what do we know about n plus 1 squared versus n squared? Well, n... So how did I get these? Is that your question? Okay, so those come from your b... So if I scroll up, the alternating series test says you have to first check. You have to check that all the terms are decreasing. How do you check that the terms are all decreasing? They're only decreasing if b to the n plus 1 is less than b to the n, where the b to the n is the thing that generates the numbers. So like what I said a little while ago was, for this example, what's the bn that generates the numbers? 1 over n squared. Okay, so our bn is going to be 1 over n squared. Now bn plus 1 means where there was an n, you have to replace it with the n plus 1, and that whole thing will be squared. Okay, so now we need to show that, that indeed that one's less than that one. So we can just compare their denominators. The n plus 1 squared is n squared plus 2n plus 1. definitely that is bigger than n squared, right? So because the denominator on the left is bigger than the denominator on the right, the left term is less than the right term. So we know that they're decreasing. So I'm going to write that in words. We know bn plus 1 is less than bn since the numerator of bn plus 1 is larger than the numerator of bn. And I need to get water. 1 second. Yes, you're right. Thank you. Angel of the box. I meant denominator. My bad. Okay. So yes, that was correct. The denominator is smaller, so the fraction ends up playing out that way. Okay. So we proved part 1 that the numbers are decreasing. Okay, part 2 is fairly straightforward. We need to show that the limit as n goes to infinity of the bn's equals 0. So let's do that. We need to show that the limit as n goes to infinity of 1 over n squared, well, we know that that's going to be 0, so you're good. So what can we conclude now? Since the terms are all decreasing and the limit of the bn's is 0, the alternating series test tells us that the series converges. Boom. Okay. Questions? I'm going to pause for a moment. I also need to spell check that. Does it make sense? You have to check the two things. Are there questions about how I showed that the terms are decreasing? Presumably taking the limit was pretty straightforward. Usually the hard part is showing that the terms decrease. We'll do another example of that. Okay. So let's do one more example. So let's say that you've got the sum from n equals 1. Oh my god, Burrito. He's angry. You've got the sum from n equals 1 to infinity of -1 to the n plus 1, so that it starts off as a positive term, times n over n plus 1. Okay, so I recommend that you split this up into the alternating part and then the bn part. So you have your -1 to the n plus 1. That's what makes the terms alternate. And then you have that multiplied by n over n plus 1. Okay, that's the bn part that we're going to analyze. Okay, so step 1 is you need to show that bn plus 1 is always less than or equal to bn. Okay, so what's our bn? Our bn is literally n over n plus 1. Right, because that's what bn is defined as here. Now, how do you figure out what bn plus 1 is? Well, I need to replace all of those n's with n plus 1. So the top part of my fraction becomes n plus 1. Let's put parentheses around it so you can see that I made the replacement. The n gets replaced with n plus 1, and then you get plus 1. So you get n plus 1 over n plus 2. Okay, so hopefully that's less than or equal to that. So how are we going to show that? Okay, so that one's a little tricky. So that's a little tricky to show that the terms decrease. There's something better that you can do to end this. What's the other thing that you have to check? You need the limit of your bn's to be equal to 0. Well, when you take the limit of your bn, you're taking the limit of n over n plus 1. And what is that limit going to be equal to? Oh, no, actually not 0. You have the same power on top and bottom. So how do you calculate the limit for that? Yes. So because the limit is equal to 1, you can't use the alternating series. So it's not that it diverges, you just don't know what it's going to be. So for this, you would say the alternating series test is inconclusive and cannot be applied. Okay. And we'll end here because that's an example of like when you can't use it. If the limit doesn't go to 0, then you don't know what happens. Cool, cool, cool. So we'll end slightly early. And I hope you all have a good rest of the day. Cool. Mm-hmm. Sure. Oh, we're going to cover that tomorrow. That's the remainder part of it. Yep. Mm-hmm. No problem. Mm-hmm. Alright. Need to stop the stream.